Welcome to the class on derivatives. But before we get into details, let us enjoy the success of our student, Akshit.
I've actually received quite a few amount of awards from my school. Number one being that I got 99% in functions.
99% in functions. Good job. What
Yes,
else?
sir. And along with that, I got an honor roll medal and the highest average across all grade 11s in my school.
What is that highest average? I didn't get this. Can you show
Uh,
me the award?
yes, sir.
I'm so proud of you, Akshit. Our approach, engaging minds, helps students to do far better as they can connect the learnings with the context, visualize strategies, apply learnings which help them to bridge the gaps. Creative thinking and problem solving is their strong point. Our students develop both mathematical and social skills. They gain confidence and get ready for future. Give the gift of education. I can be part of your success story, build strong foundation, ensure bright future. Contact on the email address given here and join my classes. Let us enjoy the lesson with Akshit. Hi Akshit, how are you doing?
Hi, sir. I'm good. How are you?
Very good, very good. So tell me what is going on.
Yes, sir. So I've actually received quite a few amount of awards from my school. Number one being that I got 99% in functions.
99% in functions. Good job. What
Yes,
else?
sir. And along with that, I got an honor roll medal and the highest average across all grade 11s in my school.
What is that highest average? I didn't get this. Can you show
Uh,
me the award?
yes, sir.
I'm so proud of you, Akshit. I was waiting for this moment for such a long time, and I'm sure in grade 12 also you'll get similar awards and admission to the university of your choice.
Yes, sir.
And keep doing so well. I expect a lot from you, like your parents.
Thank you, sir. Thank you so much.
Good job. Good job. We are proud of you.
Thank
Keep it
you.
up. Okay, so today, what do you want to learn?
Sir, today we can continue with derivatives and limits.
Derivatives and limits, calculus. You're way ahead of the class. What are you doing in the class in calculus?
Sir, in class, we're just starting to figure out what the indeterminate form is and how we go about factoring, rationalizing, substituting, and all of that.
So that is kind of pre-calculus before limits. You are around
Yes.
that first chapter.
Yeah.
Very good. So we are now in chapter 3, which deals with derivatives. So I have a lesson for you, like always, and
Yeah.
let's begin with that. So I'll share with you the lesson, and then
So
yeah. So let me just share with you. Perfect. Can you see my screen?
yes, sir, I can see it perfectly.
Perfect. So can you please read the title?
Yeah. Derivatives, Introduction Calculus. Derivatives Lesson 1, Power Rule.
Power rule. So we begin with power rule mainly. This is the simplest, and we find derivatives of all the polynomials special with the power rule, but you can find derivatives of rational functions also, right? So now you know what is dy dx. You know this
Yeah.
limit h approaches 0, f of x plus h minus f of x over a. So this is the difference quotient formula, right?
Yeah. Yes, sir.
So let me write down here, this is difference quotient. And as you know, we use difference quotient to find the limit of a function at a particular point, and it
Yeah.
also gives you the tangent at that particular line. Derivatives is all about finding tangent on a curve at a given point. And therefore,
Yeah.
we use this difference quotient formula a lot, and it is given a name. And the name given to this is derivatives. Very simple.
Yeah.
So basically, derivatives is nothing but defined as limit of the function f of x plus h minus f of x over h, where h approaches 0. That means
Yeah.
2 points are considered on the graph of the function, and these 2 points are x and x plus h away, where h is very, very small,
Small
negligible,
value. Yeah.
approaching zero. And therefore, the secant becomes a tangent,
Yeah.
and that is how we define a tangent, basically. Right? So that's the basic concept of derivatives. And today we'll learn about the notations, differentiability, power rule, constant multiple rule, general power rule. We'll take up some questions based on sum and difference. We'll see how do we calculate the tangents and normals, and also rate of change applications. We'll do all this in today's class. Okay?
Yes, sir.
Ready for it? So let's begin with the basic concepts which I was just talking about.
Yeah.
Okay, so let me erase. So here we have the definition. So I have to switch between annotate and all this before moving to the next screen.
Yeah.
So can you read this
Yes,
slide?
sir. Of course. Derivative concept. G of x equals to the limit of f of x plus h minus f of x over h as h approaches 0. Gradient of a function, the limiting value of the slope of the secant as a tangent, the limit of f of x plus h minus f of x over h when h approaches 0, is a very important concept applied in many situations. It is given a special name called derivatives.
F
F prime.
prime x is the way to write derivatives, and dy
Yep.
dx also is a way of writing derivatives, right? But basically, this is what we're trying to do. Yeah. Please read forward.
Yep.
Continue.
Yes, sir. Derivative at x equals a is f prime of a, which can represent slope of a tangent line or instantaneous rate of change.
Right. So let me just make a small sketch here to make these things absolutely clear to all our students. So when we say we are taking 2 points, let us say we are taking these 2 points. I've drawn a secant, right? This is a secant which goes
Yeah.
through point P and Q. So this what we have is a secant, correct?
Yes, sir.
So we are saying that basically the point P is x and f of x, the y value, right? And point
Yeah.
Q is x plus something, right? X plus
Yes.
something, let's say x plus x1, and then it'll be f of x plus x1, right? The y value.
Yes.
Is that okay? So what basically we are doing is we are bringing the point Q very, very close to P. And then if it comes extremely close, so that the distance between Q prime, the second point, and P, horizontal distance is very small. So let's say this now is at x plus h. Then the value will be f of x plus h. You see that?
Yes, sir.
Where h is very, very small as compared to 1. So if you closely look at it, it will be seen like this, right? So it will be seen like this, where
Yeah.
the 2 points are P and Q prime now. So these coordinates are x plus h, f of x plus h, correct? And the P point coordinates are x and f of x. Y value
Yes,
is
sir.
the value at x, correct? So
Yeah.
these are the 2 points. Now you can see that the slope of the tangent is rise over run, right? So this is the rise, which is difference of y values. That is
Yeah.
f of x plus h minus
F of x.
f of x, and this run, which is h. Okay? So
Yeah.
that is what this is, where h is approaching 0, as we said, it is very, very small. So it gives you
Yeah.
the slope of the tangent line. As we also say, this is the gradient, right? So gradient and slope are the two terms used. And also it represents instantaneous rate of change, I ROC, which you learned in grade 12 functions, right?
Yes, sir.
So that is the connection between all this. Let's move forward and look into these conventions, and then we'll move
Yeah.
forward with the example. So these are different derivative notations which you will come across. The derivative
Yes.
of a function f at a point x equals to a. Let us say that point P is at x value of a. Then the derivative at a will be limit h approaches 0, f of a plus h minus f of a over h, right? So this
Yes, sir.
tangent slow, you can find only if the limit exists, right? So first thing is
Yeah.
limit should exist to find the derivative. Very clear. Is it okay?
Yeah.
Right. So the same formula can also be written in different ways. It can also be written as f of x minus fa over x minus a, right?
Yeah.
So there are different ways of writing the formula as we have given here. Now there are two conventions which we normally follow. One of them is called the Lagrange's notation, where we use f prime a. The other one
Yeah.
is the Leibniz notation, where we use dy dx, right? Now, to write, it is convenient to write f prime a, I should say easy, right?
Yeah.
However, dy dx is more meaningful.
Yeah.
It provides additional information.
Okay.
Can you tell me what additional information it provides?
Yes, sir. I think it's saying that the derivative of y over the derivative of x.
Differentiate with respect to independent variable x. So it tells you
Oh, okay.
that this equation is differentiated with what variable? Because sometimes the independent variable could be something else. For
Right.
example, I could say dv dt. Do you understand? So I've all of
Yeah.
a sudden talking about velocity and differentiating it with respect to time. You
Time.
see,
Yeah.
respect to time, correct? So it becomes acceleration, right? Very
Yes.
so now clearly, if I keep on writing f prime a, I do not know with which
Okay.
parameter am I, differentiating it.
Yeah.
So that is an ambiguity, especially when you're using more than one variable in an equation. If there is only one independent variable, well, nothing wrong with it. Easy
Yeah.
convention to write. Let's follow Lagrange's notation most of the time, correct?
Yeah.
But when it comes to uh, derivatives like involving real life situations, we'll prefer to use Lebanese notations. Is that clear to you?
Yes, sir. Clear.
Let's move on to the next page, which is we'll now find derivative of a cubic function and
Yeah.
see, can we derive a formula for a polynomial derivatives? That's the whole
Yeah.
idea, right? So can you tell me, can you read the question, please?
Yes, sir. Example 1, derivative function and gradient at a point. Given that f of x equals x cubed plus 1, find the derivative with respect to x, f prime of x using first principle, and find the gradient of the curve at the point P, 2, and 9.
Correct. So whenever you are given such a question, first principle basically means apply this particular formula, right? Which
Yes.
is the definition of derivative. This is the first principle. Second, important things to understand. We are given gradient of the curve at a given point. We are not saying that this point is on the curve. Mind it. We are not saying that
Yeah.
this point is on the curve. 100% time student is assuming the point to be on the curve, right?
Yeah.
Normally we will do so. It is good idea to verify it, right? So
Yeah.
f of x equals to point p is 2, 9. So what is f of 2 equals to? Let's figure it out. F of 2 is 2 cube
2q plus 1.
plus 1, which is indeed 8 plus 1, which is 9.
9.
So the point is on the curve as we have shown here. But there is no
Yes.
harm in checking it, especially in the examination, because there
Yeah.
could be questions when the point may be here. You may have
Yeah.
to find with some other different conditions. You get the idea. We'll get to that example also. So,
Yeah.
well, it is safe. Very first example, no tricks involved, straightforward. But in examination, there could be a question where the point may not be on the curve. Okay.
Yeah.
So from that point, we may draw tangents to the curve. So it's a different question
Yeah.
altogether with similar result. Okay. So,
Yeah.
so we'll use the first principle, that is application of this particular formula on the function, which is x cubed plus 1. So f of x plus h will be what? Replace x with x cubed
X
plus
plus
1,
h.
right? So x plus
Yeah.
8, right? X with x cubed plus 1, x plus 8. So what do you do here basically? Since it is x cubed and you're saying x plus h, so replace x plus h with x and you get q plus 1 minus f of x, which is the function itself. Now, do you
Yeah.
remember the formula for a plus b whole cube?
Yes, sir.
So you remember. So tell me what is the formula for a plus b whole cube?
Yes, sir. It would be a cubed plus 3a squared b plus 3ab squared plus b cubed.
Perfect. Now, some students may not remember this. So I like them to look into this Pascal's triangle. You remember Pascal's triangle? Some students might remember,
Yeah.
right? So that is how you could draw a Pascal's triangle. Sorry, 1 plus 1 is 2. And then again, you continue this Pascal's triangle, right? So 1, 3, 3, 1. And then if you continue, you get the fourth degree also. You get the idea. And,
Yes, sir.
like this, any degree you can get. So that
Yeah.
becomes the Pascal's triangle. The coefficients for cubic are these 1, 3, 3, and 1. You get the idea, right?
Yes, sir.
So if you do not remember, and let us say the power is not 3 but 5 or 6, you could actually use Pascal's triangle.
Pascal's
You could
triangle.
also use binomial coefficients, right? The other option
Yeah.
is binomial coefficients, right?
Yeah.
For expanding these functions. But anyway, Pascal's is very easy to do. So you expand it, and as soon as you expand it, you'll find that these terms will cancel away. X cube and x cube cancel
X
away,
cubed.
and plus 1 and plus 1 did not cancel. Oh, there is,
Oh, no,
I
sir. It
forgot to write
cancels.
plus 1 here,
Yeah.
right?
Yeah.
So that's an error. Good, we thought. So it's very common sense, right? So when you have x plus h minus f of x, then all the
Yeah.
terms of f of x will cancel. In this case, I forgot to write plus 1, typing error will cancel.
Yeah.
So what remains and what will remain always is all the terms with h. You
With
see that?
H. Yeah.
So therefore, you can take h common, right? You can take one of these
Yes.
h common and cancel with the denominator, leaving you with the numerator, no denominator h. You understand?
Yes, sir.
So the whole difference here is that when you substitute 0 for h, you get a situation which is 0 over 0. You get the idea.
Yeah.
So when you cancel the h, then now 0 over 0 has been resolved.
It's
It is a
It's
common
avoided.
factor. Now you can substitute h equals to 0, and you'll see that these cancel away, and you get 3x squared
Yes.
as your derivative. Now you know this
Oh,
is a
okay.
general function. So what you also
Yeah.
learn here is that derivative is not a value. Derivative is
It's a
a
function.
right?
Yeah.
Derivative function. Do you mark this? Derivative is a function. And we
Function.
got a
Yeah.
function which is 3x squared, right? You know, it's a parabola kind of like this, correct? You could
Yeah.
draw it. It's a function, not a point. But at a given point, which is in this case p equals to 2, 9, substitute 2 and find the derivative at 2, which is 12, shown with the orange line in this particular
Yeah.
sketch. Does it make sense to you?
Yes, sir. Makes sense.
Correct? Very
Yeah.
important concepts you have learned from the very first example on polynomials, and that is that derivative is always a function. Very
Yes, sir.
important, correct? We have actually a general expression here which will give you derivative at any point, correct? We
Yeah.
did not use, we did not use fa minus
Yeah.
x, right? We used general formula to find the general equation. Now, sometimes we can actually have another kind of question here. That is, we say h is very, very small, right? Now,
Yeah.
I am assuming h to be 0, and therefore I wrote 3x squared as my answer, correct?
Yes.
But many times what happens, if they want the answer to 3 significant figures, approximate, or 2 significant
Yeah.
figures, you may use the value, and we may write the value as 3x squared plus 3xh. You understand?
Oh, okay. Yeah.
Approximate it to some decimal places when they say, well, h is not so small, but close
Yeah.
to 0. You get the idea?
Close to 0.
That means
Yeah.
h is 0.001, right? In that case, you may
Yes.
neglect h squared, but the other h will contribute towards a value of a secant. You get the idea?
Yes, sir.
So that is also possible in some questions, correct? So let's move on and understand what we did just now. So can you please read the note?
Yes, sir. dy by dx has an advantage since we can specify the multiple dependent and independent variables. It is normally treated as differentiation operator. Symbols capital D or capital D sub x is also used as a differentiation operator.
Correct.
Value of derivative at a specific point is indicated as f prime a or dy by dx sub x equals a. Gradient of a curve at any point is the value of the derivative at that point.
So you got the idea? So we had this
Yep.
function f of x equals to x cubed plus 1, and we wanted to find the derivative at 2, 9. So what we did was we found the derivative first, right? So f prime x we wrote like this, and the derivative
Yeah.
was 3x squared. And then at a, the derivative was what? At 2, we substituted 2 here and found the value. You get the idea, right? So this
Yes,
is
sir.
4 times 3, 12. And this is basically slope of tangent line. You get the idea?
Yeah.
Now, once you have the slope of tangent line, you can also find equation of tangent line. You get the idea? So
Yeah.
that will be an exercise for you. So the question for you is find equation of the tangent.
Yeah. So, sir, in this case, 12 would be the slope, right, of the tangent?
12 is the slope. So you can use the formula y equals to mx plus b and the point, or sometimes I prefer to use point slope formula y minus y1 equals to m times x minus x1. Did you come across this formula?
Yes, sir. Point slope format.
Point slope formula. So you can plug point slope. So y1 is given to you as 9, slope of 12, x
Yep.
minus x1 as 2. Rearrange and write the answer in the standard form. You get the idea. So y
Yes, sir.
minus 9 equals to 12x minus 24. Bring them all together. So 12x we have to keep positive, minus y, bring 9 here. So, so minus 12 and plus 9 is how much?
Minus 12 and plus 9 would be 3, sir. Sorry, minus 3.
24, 24, 24. 13.
Okay, yeah, yeah, minus 13. Yeah,
So
minus
you have to
24
take
plus
away
9.
15, right? Equals to 0. Because if you
Yeah,
take
yeah.
away, if you take away 10, it'll be 14, but you're taking away 9, so it'll be 15, right? So that
Yeah, yeah.
becomes the equation of the tangent line. Is that clear to you?
Yes, sir. Got it.
Now let's move on to another very important concept, and this is existence of a derivative. We just
Yes.
said we found one condition that derivative exists if the limit exists, correct?
If the limit exists.
But
Yeah.
you know, there is one more criteria, rather two more criteria. So first is limit should exist, correct?
Yes.
Second is the point should exist.
Oh, okay. Yeah, the point should exist.
You're saying at that point on the curve, right? If the point is not in the domain, how will I find the derivative?
Yeah.
Third is the the derivative at that particular point can be a vertical line.
Yeah.
Can be a vertical line. So vertical line is not a real value, right? So slope
Right.
of vertical line is undefined.
Yeah.
Is extremely large, right? It's not a real number. So
Yeah.
these are the three restrictions which you have to keep in mind that the derivative may not exist. You get the idea?
Yes, sir.
So I'm showing this at different levels. So it is not existing at corner. Can you tell me why it does not exist in the corner?
Yes, sir. Because if we draw a tangent to that point, the slope
Yeah.
would be like
So
that,
we
right?
could have infinite tangents at this point. You get the idea? We have this
Yeah.
particular thing. This line is a tangent, this line is a tangent, this line is a tangent. In fact, any line over here is a tangent.
Yeah.
Think about something sitting on your table, correct? Every
Yeah.
the table as a plane is tangent
Yeah.
to the thing on the table. So every line
Right.
on that plane which touches this object will be tangential to the object. Now, which
Right.
one is the right tangent you're looking for? You don't know. So that is the
Yeah.
ambiguity. And therefore, the corners are not differentiable. So we say this is not differentiable. Very important point. Is it clear to you?
Yes, sir. Not
Or
differentiable.
now in cusp, what really happens is the tangent could be infinitely large. If you look at this point right in the center, then you see that this tangent is vertical. Do you see that? You're
Yes.
approaching a very high value and becomes almost vertical. Therefore, it does not exist.
Yeah.
On a, in any object which has a starting point like a square root function, you cannot approach this function from the left side, can you?
From the left side. Yeah.
So
Yeah.
the limit does not exist at this point, right?
Yeah.
So you cannot approach. So limit does not exist, and therefore this is not differentiable at 0. Square root of x is not differentiable at 0. Even otherwise, if you draw a tangent line, it will be vertical. And so we have an asymptote, a vertical line
Yeah.
whose gradient is not defined. And therefore, we say derivative does not exist. You get the idea?
Yes, sir. Got it.
Here, we have a jump discontinuity, and so the limit does not exist, right? So we have a jump discontinuity.
Oh, okay. The left limit's not equal to the right limit, right?
Correct. And but there is another example which I left in this case, and that was a question. If you have a hole, then
Yeah.
limit exists, right? However,
Yes. Yeah.
point does not exist.
Oh, okay. Yeah.
And because of that reason, that it is not defined, derivative is not defined at the given point because it's a hole. You get the idea.
And the
Limit,
function won't be differentiable, right, sir? In that
yeah.
case?
So now what you learn is very good questions. One is, can the function be continuous, still not differentiable at a point?
Yes, sir. It can still.
These two examples, functions are continuous and not differentiable, right?
Yeah.
And the limit exists. Limit exists, but still the
But
function
the
is
point.
not differentiable. Do you see that? So these are
Yes,
two
sir.
very important questions which are asked in communication section. So
Yeah.
true or false, or provide reasons or an example or a contradiction to show that
Yeah.
your answer is correct. You get the idea?
Yes, sir.
So it could be like, if the limit exists, then the derivative will also exist. This statement is not always true because
Right.
if there is a hole, then the limit will exist. However, it is not
The point.
differentiable at that
Yeah.
point because that point is not in the domain of the function. How will you draw a tangent at that point? Correct? You cannot.
Right. Yeah.
Makes sense? Good job. So now let's move on and derive the very first formula for finding derivative, which will make our life so easy. Applying
Yeah.
this question formula is not easy. You have done a lot in the previous chapter and you know how difficult it is,
Yeah.
correct?
Yeah.
Ah,
It's very long.
very long method. We have a very shortcut method. So we will find a general rule and we'll
Yeah.
take up a power function. Power function is
Right.
to the power of n, where n normally is treated as a whole number. You get the idea?
Yes,
So
sir.
where n is a positive integer in our case. Derivative of this is n times x to the power of n minus 1. You did see
Oh.
or observe
Yeah. Yeah. Yeah.
that the derivative is 1 degree lower, correct? Most of the
Yeah.
time.
For the cubic function. Yeah. Yeah.
Because quadratic, for quadratic is linear. For linear, it is
Yeah.
it could be a constant, and for constant, it is 0. 1 degree lower. So this is
Yes.
what we are going to derive from the very basic definition. We say, what is f prime of a? That means derivative at a. By the
Yeah.
definition, is f of x minus f of a over x minus a, where x approaches a. Correct?
Yes.
Now, in our case, the function is x to the power of n. So we have x to the power of n minus a to the power of n divided by x minus a. Correct? Now,
Yes, sir.
there is a formula which relates what is x to the power of n minus a to the power of n equals to. This is the formula which is written here. It is x minus a times x to the power of n minus 1 plus x to the power of n minus 2a plus so on, x to the power of n minus 2 plus last term will be a to the power of n minus 1. So that is the formula which is applied here, right? This formula is very well known. So we are not getting into derivation of the formula. You should know it.
Yeah.
And once you apply, you know, x minus a cancel. Now, since x minus a cancels, it is not of 0 over 0, right? Earlier, you see,
Yeah.
if I put 0,
Yeah. Yeah.
I mean, if I put a for x, I get a to the power of n minus a to the power of n over a minus a, which is 0 over 0.
0 over 0.
Wait a minute. Now, once I have cancelled the common factor, I am left with an equation where we can now substitute x equals to a, correct?
Yeah.
So let us do that substitution. So once you substitute x equals to a, then you get all the terms in terms of a to the power of n minus 1, because you know
Yeah.
when you expand a binomial thing, right? Binomial coefficients, they sum up to the same thing, right?
Right.
So now you have how many of these? You have n of these with a to the power of n minus 1.
N minus 1.
Therefore, we get a general formula that the derivative of the function, so I missed slash, derivative of the function is n times x to the power of n minus 1. So if the function f of x is a power function x to the power of n, then the derivative of this function is basically n times x to the power of n minus
N
1.
minus 1.
Perfect.
Yes, sir.
Now, in the next section, we will extend this power rule and we'll say, well, if it is a constant times this, then this will be n constant times n times this, right? Because the
Yeah,
derivative of a constant, it doesn't matter. It's a scalar multiple, right? So if you have this
right.
gradient here of a function, it remains same. Perfect. So if it's
Yeah,
constant times x to the power of n, then that is the one. So that is another formula which you could note down. So we have learned two
yeah.
formulas just now. Now, based on this, we have a question for you. Can you please read the question?
Yes, sir. Find gradient using power rule. If f of x equals x to the power of n, then f prime x equals nx to the power of n minus 1. Find gradient at x equals 1 using your result in part I, and verify your result by drawing a tangent at x equals 1.
Correct. So that is the exercise. I have done one of the examples for square root of x. Square root of x means x to the power of half, correct? So
Yes,
we have written this as square root of x is x to the power of half. Applied the formula, which is n times, n is half for you. Half times x times n minus 1 means half minus 1. Half minus 1 is minus half, right?
minus half.
You get 1
Yeah,
over 2 x to the power of minus half, which can be written as 1 over 2 square root x. Is that clear to you?
yes, sir, clear.
Right. So that becomes the slope or the gradient at any point. You will observe what happens when x is equal to 0. You get 1 over 0, right? It is not
Yes,
defined at origin, just as we saw initially, correct?
yeah,
It is a
right.
vertical line which is tangential at 0, and slope of a
Yeah,
vertical line is not defined. And these examples are easy. F prime x will be what? Equals to 2x. You see that how
2x.
easy it is? And here
Yes,
we have x to the power of minus 1. Tell me what is the derivative for this?
sir. So for this one, I was actually initially a bit confused when looking at it. So would we put an exponent of 1 at the top for 1 over x to the power of 1 and then bring it down again?
Yeah, so minus that exponent minus 1, x to the power of minus 1 is minus 2. Do you see that? So that is what we get. So it is 1 over x squared. Is that clear to you? So
Oh,
that
okay.
becomes the derivative of the function. And so we can now, at 1, you can draw the tangent line as the question demands. And you'll
Yeah,
find that these tangent lines have the slope, which is as calculated, right? So f prime of 1 will be what? 2 times 1, which is 2. Is it okay?
yeah,
So we can figure this out. Okay, so is this point very clear to you?
yes, sir.
Next is the example which I was talking about. If we multiply the function with k, then the derivative also gets multiplied with k. You can take out this k because k is independent of h, right?
Right, right.
And therefore, in the formula, you get a multiplier with kgx, right? And
Yeah,
that is what it is. Now, there are two more rules. One is called the sum rule, and one is the difference rule. If I have a polynomial with many terms, then each derivative can be added together or subtracted.
right.
That is the sum rule and the product rule. Oh, I mean, the difference rule. Okay. Now let's move on and take up more examples. Here is a test question for you. You can
Yeah,
see from here, the question is determine the equation of tangent at p equals to 1, 3. So we're given a point. If I substitute 1 here, right? So 1 cube root
yeah,
is 1 times 3 is, so this point is on the curve
yes,
of x equals to 3, cube root of x squared, correct? Now you have to find
yes,
the tangent line. First step, find the derivative, right? So I wrote,
yeah,
it is to write it as a rational exponent because, 2 over 3, right?
yeah,
So derivative will be 3 is a constant, right? So 3 is a constant times the power n, which is 2 over 3, x to the power of 2 over 3 minus 1. You get the idea? Apply the
yes,
formula.
sir.
And once you simplify, you get 2 times x to the power minus 1 over 3. So you could write this as your result. To find the derivative at the given point, substitute the value of x, which is 1, and you get 2 over 1, which is 2. 2 is the slope of the tangent line. Now you can
Right.
apply the point slope formula and write down the equation of this tangent line. Does it make sense?
Yes, sir. Got it.
Correct.
Sir,
Can you yes, sir.
just a quick doubt though.
Yeah,
When we were doing the power rule, right, to find the derivative, can we go over how we actually use the constant in this case?
correct. So let me do this question again. F of x is equals to 3. x to the power of 2 over 3, correct? Now 3 is a
Yes,
constant,
yes.
right? So the derivative will be what? So derivative of this function will be the constant 3 times the power 2 over 3, correct?
Yeah,
X to the power of 2 over 3 minus 1, correct?
minus 1. Yeah.
So this 3 and 3 cancels. We get 2 times x to the power of, that is 3 minus 2 minus
Oh,
3
minus 1 over 3.
minus 1 over 3. Is it clear to you?
Yes, sir. Got it.
So we get 2 over cube root of.
Cube root of x.
So that is how we are going to get this particular result. Is that clear to you?
Yes, sir.
You have
Got
to
it.
go systematically, right? And now you plug it in, that value of 1, because you want the slope at point x equals to 1. And clearly this is 2 over cube root of 1, which is 1, right? So you get 2 as the slope. Substitute
Yeah,
the value 2 in the point slope form. You can use y equals to mx plus b also and get
yeah.
your. Is that clear to you?
Got it.
Now read question number 4. That is another question for you. Yes, please read.
Yes, sir. Determine the equation of the normal at P. Find x-intercepts of the normal and the tangent. Find area of the triangle PQR, where Q and R are the x-intercepts.
Very important question. Make a note of this question. It is
Yes,
a
sir.
test question, examination style.
Yeah.
Do you understand the question? Determine the equation of normal at P. So when I say normal at P, then this is your tangent. The slope will be negative reciprocal. You get the idea?
Sir, oh, okay, that's the point. Yeah, yes.
So normal at P, find the x-intercept of the normal. So when you extend this line, you find the x-intercept of the normal. You get the idea?
Yes, sir.
Find the x-intercept of the normal and the tangent, right? And the tangent x-intercept is this. Find area of triangle PQR where Q and R are x-intercepts, right? So Q and R are x-intercepts. You get the idea? So you have
Yes,
this
sir.
triangle, you have to find area of this triangle. That is the question. You understand? So
Yeah.
we have extended the question to part C and D, where you have to find the equation of the normal at P. Then you find the x-intercepts of both the normal and the tangent. So you got 3 different points. Now with 3 different points, you have to find area of the triangle. And of course, it's simple because this is a right angle triangle, right?
Yeah.
So these two lengths, when you multiply, divide by 2, will give you the answer, right? So the area will be equals to, let's say this point is P. So the length PQ times length PR, correct? Divided
Yes.
by 2. That gives you the area of this right angle triangle. It's a very important question from test point of view. Do you get it?
Yes, sir. I got it.
Very good. So let's move on and look into another very important concept which we are going to use in chapter 6 on curve sketching and in chapter 5 in finding maximum and minimum for a given graph. So very important concept. Can you please read the question?
Yes, sir. Example 2, equation of tangent line. Find the points on the curve f of x equals negative x cubed plus 3x squared minus 2, where the tangent is horizontal.
Horizontal tangent means what? Basically, on this curve, the tangent will be horizontal on a turning point. Do you see that?
Yes, sir.
So with
Turning
this,
points.
we get the turning points. And what does turning point gives you? Turning point also gives you local maximum and minimum. Do you understand?
Yeah.
Local maximum and minimum. In this case, this becomes max and this becomes min. You get the idea, right? So
Yes,
we
sir. Got it.
have understood lot of details about a curve. Where does it turn?
Yeah.
What is the maximum value? What is the local minimum value? Sometimes when it is a degree 4, even degree polynomial, we also know the range of the function. You get the idea.
Yes, sir.
Many parameters will be solved just with this kind of an example. The concept is simple. Horizontal tangent means that the slope or the gradient is equal to 0. So we are going to
Yes.
equate the equation of the derivative to 0 to find the x values which will satisfy this equation. So in this particular case, so what have we done? Can you please read the solution?
Yes, sir. So basically, we use the power rule to find the derivative. And then since we know that the slope of the derivative is a horizontal tangent, which is 0. We
Yeah.
simply plug in f prime x as 0 and then
Correct.
solve for x.
So you got two values, x equals to 0 and 2 as expected. One of them is a minimum, the other one is maximum. Substitute 2 and 0 and find the values or the x or the turning points of the curve. You get these ideas? But
Yes,
this
sir. Wow.
is a very beautiful question, starting point for questions to come in future. You get the idea?
Yes, sir.
Okay. Now let's look into rate of change example. Can you please read this question?
Yeah. Rate of change. A spherical balloon is being filled with air. What is the rate of change of the radius of the balloon when the area is changing at a rate of 80 pi centimeters squared per centimeter?
Correct. Remember, I have not cancelled the units. Units are centimeter square per centimeter. Some square
Yes.
like centimeter. Doesn't make sense.
Yeah.
So, what is the rate of change of the radius of a balloon when the area is changing at the rate of 80 pi centimeter square per centimeter? You understand? Area
Yeah.
over the radius. That is the rate of change with respect to radius. You get the idea? Now,
Yes, sir.
very important question. So it says surface area of a sphere, you know the formula, 4 pi
Yeah.
r square, right? Now,
Right.
you know, so it's important to write the convention in the function notation. A as a function of r is 4 pi
Yeah.
r square, where r is the radius, right? So the derivative with respect to r is 8 pi r, correct? 2 times
Sir.
4, 2 times 4 is 8.
Yes. 2 times 4 is 8.
So
Yeah.
let me write
8
area
pi.
as 4 pi r square. The only variable here is r, the others are constant, right? So the derivative for area will be 4 pi times 2 r. Do you understand?
Yes.
2 times r, 2 minus 1 is 1. So that is 8 pi r is my area, which I've written here. Now, it says, so 8 pi. The spherical balloon, what is the rate of change? What is the rate of change of the radius of the balloon when the area is changing at this rate? So we have
Yeah.
the rate of change of 80 pi. So rate of change is 80 pi. Do you see that?
Yes, sir.
So we have to find the radius. It is a reverse calculation. Do you understand?
Yeah. They gave us 8 prime r.
We have given you the derivative and you have to find at what point that derivative value exists, right?
Yeah.
So we are finding the value of r. So 80 pi is equals to 8 pi r. Simple calculations in my examples, but big concepts. And from here, you can find the value of r as 10 centimeters. Does it make sense to you?
Yes, sir. Got it.
Question number 6 is for you. Can you please read the question, make a note, and then solve and submit? Yes, please read.
Yes, sir. Find the rate of change of volume of the balloon when the radius is changing at the rate of 80 pi centimeters squared per centimeter.
We have changed the question from area to volume this time. You get the idea? So
Yes,
find
sir.
the rate of change of volume. Find the rate of change of volume of
Yeah.
the balloon when the radius is changing at this rate. Do you understand? So
Yes,
we
sir.
change this question a bit, but makes things very complicated. And that is
Yeah.
beauty. When you see a question, you have to see the question from different angles to really master the techniques of solving questions. Do you see that?
Yeah.
So first step, you'll find the radius. Then you know the volume is 4 by 3 pi r cube, whose derivative
Right.
is 4 pi r square. You know, that's very important. So rate of change of volume is same as surface area formula. That is also a question sometimes. So we know the volume is 4 by 3 pi r cube, right? And what is
Yeah.
the derivative? 4 by 3 pi
Pi r squared.
r square. So 3 and 3 cancel. So you get 4
Right.
pi r square. Do you see that? So
Yes,
rate of
sir.
change of volume is rate of change is surface area. You see?
Yeah.
So, very good formula and you can work on it.
Yeah.
Perfect. That brings us to the end of the lesson today with these remaining test questions for you. So
Yes, sir.
I'd like you to pause the video with all the audience, copy these questions, and then solve. Correct, Akshit? Let us
Yes,
discuss
sir.
them. Can you please read? Applications with tangents and normal. I've taken these questions from previous test papers, and I'm sure some of them will be in your test paper also. Okay,
Yeah.
please read question number 7.
Find the point on the hyperbola xy equals 27 where the tangent line is parallel to the line y equals negative 3x plus 2.
How will you solve this question?
So If the tangent line is parallel, then we know that the slope must be the same.
Good. So we know the derivative f dash x is given to you as minus 3. Brilliant. Now,
Yeah.
how will you find derivative when the equation is given to you as xy equals to 27? Tell me.
So you can write it in terms of y, right? Y is
Beautiful.
27 by x.
Beautiful. That's why you are number one student. So 27 over x, which is x to the power of minus 1. You can now find the
Yeah.
derivative and do question number 7. That is a good hint for the students who are still. See, remember, Akshit is doing limits at school, right? And we are working on derivatives, chapter 3. Beautiful answer. Question number 8, please, Akshit.
Yes, sir. Find the equation of the normal to the curve y equals negative 8 over x plus 5 at the point a 2 comma 1.
Correct. So as I said, this point is on the curve. You should test it, right? It is really on
Yeah.
the, and this is like an extension to this question, but this time we are working on the normal. So we're giving you practice. We found the tangent first, and now we are normal. Normal means negative reciprocal should be the slope, correct? Question
Yes.
number 9, please.
Find equation of the tangent and normal to the curve f of x equals x squared plus 2x plus 1 at the point a 0 comma 1.
Correct. Part B.
Part B, find the x-intercepts p and q for the tangent and normal, and find area of the triangle APQ.
Similar to the question we did
Yeah.
in one of our examples, you should be in a position to do it. Question number 10, please.
Find the equation of tangents to the curve y equals negative x squared plus 2x, which pass through the point p 2 comma 9.
This is the bonus question for you. Can you please check if the point is on the curve?
Yes, sir. So if we plug in 2, then we get negative 4 plus 4. So the point would not be on the curve, sir.
The point is not on the curve.
Yeah.
This is a bonus question. But now, Akshit, I'll tell you the key in reading
Yeah.
the questions, right? Can you please read the question once again?
Yeah. Find the equation of tangents to the curve.
Tangents.
Oh, it's a plural. Yeah.
Plural means there are more than one tangent. There are
Yeah.
more than one tangents.
Yeah.
With one point on the curve, you can make more than one. Then the function is not defined, right? Like an
Yeah.
absolute function where you don't have derivative. Then the
Right.
only case could be that the point is external. You understand? So it's kind of a parabola going like this. And now you see the point is external and you can draw these two tangents. Do you see that? We are given a
Oh,
point
okay.
outside. And we're telling
Yeah.
you to find the equation of both the tangents. That is the question which I was talking about right in the beginning. And be
Yeah.
prepared for this question in the
Yeah.
okay. So
Yes,
we'll
sir.
end our lesson today at this particular stage, and I'd like you to summarize today's learnings. Yes, Akshit.
Yes,
What
sir.
did you learn today?
Well, sir, today was definitely a big learning experience because starting off with different quotient in advanced functions, it's a very long process, right? But thinking that you can find the derivative just like easily with the power rule makes life much more convenient, right?
Yes.
Yeah. And along with that, the applications that come along with derivatives, I can see like the how it can be related to like volume, area, velocity, and everything. So I think mastering the power rule can really help me in tests. And also I really like the triangle questions where you can actually use the tangents to find the area. So I found the entire experience really interesting.
That's great. And also, a simple question of horizontal tangent line can
Yes.
tell us about the turning points on the curve, and later you will learn how do you find local maximum, local minimum just by finding this point, right?
Yes.
Turning
Yes.
point. And also in curve sketching, we get a very critical point on our graph, all the turning points, and then we can easily sketch the graph with the help of intercepts and the turning points. You get the idea.
And the turning points. Yeah.
So there was a huge learning for a student like you who can interpret and then apply them to the right context. So our whole idea here is to understand the basics, right? And
Right.
how we can apply these basics, scale them up as we move
Right.
forward and solve questions like nobody's business, right? That is what we're going
Yes.
to do. And I hope it was worthwhile.
Yes,
This
sir, for sure.
I really enjoyed with you. And you were bright in answering some of my questions, which I thought
Yeah.
may not be in a position to answer, but did a good job. Okay, great. So we'll end this here. Good night and see you again in the next class.
Thank you, sir. Thank you so
Thank
much.
you. Bye. All the best.
Bye.
You can always join my classes by writing to me on the email address given. I can be part of your success story and build strong foundation to ensure bright future. Thank you.